So this is week 7 and lecture 8. So today marks the real beginning of robust and optimal control. So, so I'm going to focusing on uncertainty characterization or modeling. I told you, uncertainty modeling sounds like not very logical, okay? So we can see characterization, okay? And there are some popular things, quantification, okay? In some of other subject areas like UQ, it's called uncertainty quantification is some sort of hot topic. Okay, in some applied math, uncertainty quantification. Okay, but I believe that modeling makes better sense because when you do modeling, do you guys know what are the purposes for modeling? There are 3 purposes for modeling. Okay, you model for what? You model for prediction. Okay, you model for control. Of course, you can say diagnosis. Diagnosis, okay? And you model for what? Do you still remember? What's the last purpose? There are 3 purposes for modeling. Modeling for prediction, modeling for control, closure control, and what is the other one? You return back to me. What's the other one? Come on. So you just think about emulator. You want to do an emulator, you need a model, for training, job training, for education. Make sense now? So in the future, say immediately have 3 purposes of doing modeling. Okay? So modeling
for fun.
Sorry, for fun is everything is eventually for fun. Everything is eventually for fun. Okay? So I think for fun is a good motivation, okay? Eventually, I said eventually for fun, okay? Eventually. So today we are going to talk about uncertainty modeling. It's a very thick chapter. We're going to spend 1.5 weeks on this, okay? It takes a long time because I said for control, I said control is an area full of interesting things because in a control, you do what do you want, what do you want, what do you have, okay? Okay, what do you have, what do you know, okay? So these are the 2 questions. I want this, I want that, can be a lot of, could be many different objectives. I want this, I want that, okay? There are also many different knowledge types about your model. So I know this, I know that, or I know the model in this form or that form, okay? So together, you have a lot of combinations. That's why control area is very exciting. And it's always exciting. Because there are always some new desire coming out. Maybe there are some new description of the model. Previously, we thought getting that part of the model, that depth is so expensive, so formidable. But now it's easy, okay? So then there are new control challenges in front of us. Okay, so there are a lot of opportunities. So control subject area for research is exciting, it's endless. And so I said control, but we have modeling here. Okay, modeling here. We have 3 objectives. One of them is for control. And for this modeling part, we also need to talk about uncertainty for sure. Okay. So one of the ideas is called Divide and what? Conquer, yes. Divide and conquer, okay? Divide and conquer. What do we mean? Because if you have a system, you have a system, and you have two parts, okay? So you have nominal model that you know. So we usually use this one in our book in the future. We call this is M matrix. Okay. Of course, the M could be dynamic. We know that it could be square or non-square, square or non-square transfer function matrix TFM. Okay. So let's draw that. The key idea of robust control for starting from this chapter is we assume that we can divide the system into two parts. One is called MS is nominal. Another one is called delta of S. This is called uncertainty. So we draw a line between this. So we divide and conquer this guy. Or we separate knowns and unknowns. So these are known, these are unknown. Okay? Unknown. Okay? But in reality, we are always giving a system that is the whole thing like this is together. You need to learn how to divide them. Okay, how to divide. Then you can conquer it. So this chapter will give you very important systematic way to separate these knowns and unknowns. Okay. Again, there are many ways to describe this. There are also many ways to describe this. We have learned in our previous weeks that many ways describe the system. We have state space. We have transfer function matrix. We also discussed about Macmillan form. Okay. We talked about even coprime factorization format, and so on and so forth. And in between, we talked about the conversion between them. One of them is called realization. Giving this one how to realize the state space. In the space, we talk about minimal realization, we talk about balanced realization, and by the way, we also discussed Hankel singular values. Then rank them, we truncate the tail, and we can easily do model reduction, right? So the reason we do model reduction, we know that how much we cut off. The bound can be very precisely known, okay, what we ignore. So that's the separation part. But today, I'm going to show you that the robust control is basically doing this. So you have an internal description of this one, okay? Your internal connection, you have a connection, interaction with your known and unknown parts. And we need to understand how we can pull out, okay? Pull out and separate, and divide and conquer. But on the other hand, you know that the overall is a real system. So you know that you have some signal that you have some of the, what we call performance probing or performance testing signal input. And we have something called Z. This is output variable vector of we care about, okay? We care about. So then this is for performance measure, okay? Performance measure. So this in and out for performance measure. On the other hand, we have another setting here. So this is a real control signal coming in, and you have real measured output Y. Okay, And this y will go to a box here, it's called K. So remember, given the system, you can separate them. Okay, so you have knowledge of this one, you have little bit of knowledge about this, not full knowledge, but partial knowledge about this. So this is something you can really change, okay? You can change. So this raised a question about robust. Versus robust performance. Okay, so RS versus RS versus RP. Let me give you an example. Okay? Let me give you an example. So suppose I didn't consider this. Okay? I don't have this one. Suppose I don't have this one. I only have a model. I designed a control which is stable, but I need to ask a question, how stable? In other words, if I perturb the system with delta, if the delta is not 0 here, so then we can use this one to evaluate how robust of the controller you design it is. So then we can ask the question, how robust and how stable? The same question. Answer. Then we can say, under the stability condition, what's the biggest size of this one? Could be how much uncertainties I can tolerate such that I can remain stable, remain within my performance index. So this is called RSRP problem, robust stability and robust performance. So if you feel like previous training in your controllers, I give you a model, you design a controller, satisfy the specification, and it is stable, okay? That's not the end of the story. It is the beginning of the story. You should continue to say, yes, good. You design a K, make this whole system stable and meet the performance requirements. Good job. But if you make this one work in the real system, you have to consider, do you have the robust stability performance? Do you have the robust performance property? So that kind of robustness issue, so meaning even if I have perturbation uncertainties here, my performance is still satisfactory under that bound. So that's called robust performance or robust stability. So I would like to say today, if you do control research without discussing robust stability and robust performance issues, then you should not publish it. So it's not publishable. You have to talk about this. So this picture is the overarching system picture of a robust and optimal control. And you may wonder, say, hey, I never thought that there's a W in here. But in many cases, you simply say, oh, this is the same. You just say, pull out this one here. You can simply say this is the same, not a problem, okay? But on the other hand, if I pull out this one, this is more general, right? So this is more general. So it doesn't excluding the case for W is U, Y is Z, fine, okay? Fine. So don't feel like, whoa, we are adding something more here. Because this will give you better flexibility to define what is the testing signal, Because you want to check the performance, you want to insert some testing signal. May not be exactly the control purpose, it's for performance evaluation purpose. Make sense? So W could be different to you. And Z could be different to Y. Because you may add some filters here, you know, to become a Z, right? So then you emphasize the frequency range of interest, and so on and so forth. Okay, so our today's job is to focusing on this part. For this control design, stable and optimal design is next chapters. So we'll focus on how to get this delta of S, how to describe it. There are many, many ways. And this chapter is the very important chapter for everybody here to embark to the journey of robust control. Okay? If you miss this chapter, it's difficult to catch up. So please pay attention. That's why I'm recording. So you can go back and read my preface of this picture. And this picture is very important. Perfect. So there are many topics on this chapter 8, uncertainty and robustness. So I already mentioned about the robustness. We'll see. So basically, we have uncertainties here. So we call P is nominal model and K is a controller. I use M and K, it doesn't matter, okay? So then the P delta is the real system model, transfer function matrix, nominal model, and here this is uncertainty. In here, you remember we are using a W of S. Okay, in W of S. This W of S is none. Okay, we add this like a filter. The reason, or we can say this is for scaling. Okay, such that we can simply say this delta. I do not know this delta. I know nothing about this delta of S, except I know only the maximum singular value is less than 1. Okay? Okay? But in reality, it's, I should be less than 10. Can you? Sure, you can, but you can move the 10 to WS, right? WS is none. WS is none, okay? WS is none. So this is additive format. So the uncertainty all in this delta, okay? So then you can also write down in this format. So this is called, this is additive, okay? So this is called what? Called matched, matched. So this is also called matched uncertainty. This is unmatched uncertainty. So in other words, you cannot pull out a P from here. You cannot pull out a P. So in other words, this one will kind of like entering the same channel to P. I'm not sure you are confused. I'm going to show you in a minute, okay? So basically, this is kind of additive, okay? This is kind of additive. And this is kind of multiplicative. And in the literature, this is called matched uncertainty. This is called unmatched uncertainty. Okay, so what do we mean matched? So let me give you one example. So remember in the classical case, you have a P, you E, you have C in here, okay? So when I say I have, in this case, I have uncertainties, that means I have something like this. So I have a W as delta S, I have something here, inside here. So this is my uncertainty, right? This is my uncertainty. So this is called not matched. What is a matched uncertainty? Matched uncertainty. It is going through the same channel. So that channel is something like this. So you have P, okay? You can pull out the P. So then you have something here, okay? So you have something here. So you cannot. So this one is I plus W delta, okay? So this is something you can pull out like a gain variation. It's not exactly true. In Seiso case, yes, it's like a gain variation, but in here, it's not a gain variation, okay? It's just on top of that. So this can be regarded as a gain. So you can pull out this one. So in some times, this is called matched uncertainties. Okay, matched uncertainties. All right, so.
Match is that you call gain variation?
I call it gain variation. To me, you can equivalent to like the gain is changing. Yeah, gain uncertainties in Seiso case. Okay. All right. So this is additive. This is multiplicative. So then, if nominal stability is called NS, so you design the K to stabilize nominal P. Okay, and you have one controller stabilize one plant, okay? 1-to-1. What is a robust stability? Is K stabilize every plant. How many of them? Most likely infinite many in this pi, okay? This pi. While this pi is a set of all models. So nominal performance is the same and satisfied for nominal plant if the performance objectives are satisfied for everybody in this set. So this pi is the set of the
family plants.
Family of plants. And usually it's infinitely many. Okay, you just say how many of the delta satisfy sigma bar is less than 1. Infinitely many. Okay. There are some visualization, you can see that, oh, you have a nominal model, but if you check the model many times, it will live on this band, okay, on this band. So, and the actual model, one of the many in this set, positive like this, okay. So that kind of, instead of the nominal model is one line, but now it's like a strip, okay. So that's a typical nonlinear, uncertain cases. And what's the origin of the uncertainty? That's a very good question. I don't know yet, but it could be from time varying factors. Okay, changing due to temperature, humidity, or whatever is changing, or some nonlinearities. Okay, or the uncertainty is due to what?
Ignored complexity.
On purpose model truncation. Because otherwise I'm going to leave with a very big model. I want to truncate some of them, so that's the purpose. So there are multiple reasons that you have to consider this band of set of pi. So pi is a set of a family of models with infinitely many members. So you need to design only one controller to control infinitely many the system, and then you can still maintain the stability and keep the performance as you wish. So that's a wonderful work for robust and optimal control. Okay, so it is really interesting to learn. So MPRP is performance, NSRS is. So we probably previously will learn some skills in CISO or MIMO control. Probably is mainly focused on what we say nominal performance design and nominal stabilization stuff. We probably only learn those things. Okay. So let's see an example. So it's more interesting, and let's see a CISO example. So this example shows that I have a transfer function, I have a numerator, denominator. Then I have some parameters alpha and beta. I know that alpha, beta, they change in this interval. Then I'm trying to write down what is my nominal model. Okay. Then I pull out this one, and so that make this delta less than 1, and I need to find out what is this W. So the W will be interesting because the middle term is 0, so I just put 0 in the middle. Okay. I want to warn you that put this one in the middle may not correspond to P0. Okay. Just by chance, this is the case here. But in principle, how to choose P0? There are other criteria. Okay. But in this case, you will just use some intuition. So because this is changing from -1 to 1, so the middle is 0. I put 0, 0 in here. I got nominal model. Then this is my nominal model. Then I put the 1, 1 is on the edge. Worst case. This again may not be right. Well, we will see. We'll see. So then we are going to get this delta in here, and there is the WS. And this delta, just to pull out, so the frequency response of this guy is something like this. Then you find out some disk to cover that. So this is called disk covering, circles. Okay. So this is a nominal model in the middle. So then at different omega, you have a W in here. Okay, you have W. Then because of the W, you can have the delta, and with the different size of delta, so basically you are allowed to do less than 1. Okay, less than 1. But this radius of this one is dependent on your frequency for sure. Okay.
What is delta here again?
Delta is just simple. The radius. Yeah, it's a simple radius. So let's take a look at the next one. Probably will give you a better idea of delta. Okay, this is for additive case. So that we always can make sure everything for all alpha, beta, this is a member of this set. And delta is anything that is less than 1, maximum singular 1. But in our case, the delta is a scalar, any number less than 1. Okay. So, but this is one way to do the separation, divide and conquer. Okay, we divide the known part versus unknown part. Okay. But the question is, you have more than one ways to do the job. There's another way you can do. You can assume you have delta 1, delta 2. You have W1, W2. So then this is your set. To make the delta I less than 1. With W is the absolute value in here. So if you do this bounding, by doing this type of divide and conquer, you might have certain level of conservatism compared to this one. This is like tight. So you can see that if the uncertainty set is too conservative, meaning it's too large than necessary, then your control design will be more challenging. And your performance trade-off, so we actually can achieve this performance, but because of the set is too big, too conservative, then you say, oh, I cannot achieve it in a robust way. So therefore, the divide and conquer is an art. Okay. So far, we still don't have what we call optimal way to divide and conquer, given the problem. So it's dependent on your knowledge about the domain application domain. So it's a domain knowledge. So just show you these two different divide and conquer, those are different. Conservative. Okay. This is an example people did in first order plus delay. First order plus delay. So then, what if you have three parameters in here? They are all inside the interval. The delay is 1 to 2, 2 to 3. So, what is the nominal value? The nominal values go in the middle. Everybody is middle. Okay. What do we mean middle? Okay. So that intuitive middle point may not be right in MIMO case. Okay. So again, I remind you, we do this one is because we feel this is in the middle. We choose that way. But in general, it may not be in the middle. Okay, the nominal model may not be in the middle. Okay. Okay. So we are going to see more advanced concept talking about the middle. Remember, I'll just give you an idea. So you have a shape. What's the middle of the shape? People say this is center of gravity is the center, right? Or center of something else. Okay, may not be at the center of gravity. Okay. So how to define the center? Remember, in the advanced topic, we may not choose in between the numbers. Okay, so some other framework to define the nominal or average. So the distance. Okay, what's the mean distance? What do we mean distance? So in this case, we can do additive part. So it's original model here minus this one. We try to use additive weighting WA. So how we can get this real and imaginary part to see the coverage, uncertainty delay system and a nominal system. So this is just a nominal system. And all the others must be within these templates. At different frequency, there's a different shape. Okay, in the shape. But you may say, oh, this looks not straightforward to me. How can I draw these things? Okay. Fortunately, there's a tool that is already done for you. So this is for what is delta A and WA. Say for example, you use 50 points, frequency points, and second column, and actually the corresponding magnitude response for all these inputs. And VPAC, you just pack those varying metrics together. MAC, VPAC, okay, pack this together. You fit this magnitude, you get a WA, okay, you get a WA. then you do ABCD, unpack this unpack this one, so you will get state space ABCD, and you also can state space to ZP, so 0, pole, and gain. So ZPK, 0, pole, and gain. Okay, 0, pole, and gain format. So then you can get those delta M and delta M. So these are the bounds. Okay, solid one is the bound. Upper bound is here. Okay, bound is here. Those delta M's are those dashed lines. Here is also you have a bond. So that's because of the scanning different parameters in the interval, you will generate that. Okay, so there are many different situations. So in this case, you can simply generate a weighting matrix WA like that, and you can plot the WA. You also can do a uncertain delta. So this is called a multiplicative uncertainty, delta M. You can do WM. So all these things can be obtained via the scanning, via the code. Okay. So this part is based on SISO transfer function, but in the MIMO case, probably it's not that simple. But the basic idea is similar. Okay, it's similar. You need to divide them. But specifically giving a problem how to divide them in the optimal way with smallest conservatism, that's still a topic of research. Okay? So, but we do have certain systematic way to handle this divide and conquer problem. Okay. So if I make a nominal model in here and the system will have delta in here, so how I can say the system is already stable or not, okay? Stable or not. So basically I can write in this this two input, so input from here and input from here, you have error in here. So any system can be written in this format. And remember, we always use positive sign here. Okay, positive sign here. So this probably is the most important theorem we need to remember. It's called small gain theorem. Small gain theorem. And this is in vector form. This is matrix. Okay? And M is P times Q. RH infinity, you know the space is called all rational stable transfer function matrices. Okay? In this PQ space. And of course, all giving a transfer function, we can check whether it is well posed or internally stable. Then we connect everything. We are going to see. When we can claim this interconnected system overall is well posed and internally stable. So I hope you see that this is a loop. And I will assume the worst case infinite norm is a worst case norm is gamma, and the other guy is 1 over gamma. So this one and this one multiplied together, it should be less than 1. So less than 1, that kind of concept, the loop gain, worst case less than 1, is called small gain theorem. In other words, if you have a loop and the loop gain is less than 1, there's no chance for this loop to be unstable. In the SISO case, So if you have a less than 1, even if your sign is reversed, becomes positively reinforcement, but it will not add up. Okay, it will not add up to explode. It attenuates. You see what I mean? So that small gain theorem is very obvious conceptually. So you have some signal, then it becomes attenuated, and that something to the power of n. N is like the rounds. Then the base is less than 1. Then something less than 1 to the power of n is converging, right? So system will be stable. So that's the case. That's the case. So it is. You can see if you have infinite norm less than gamma, then this could be less than or equal 1 over gamma. Then if m infinite norm of this one is less than or equal gamma, then this has to be strictly less than 1 over gamma. Okay.
I don't understand this block diagram still. I mean, why? I mean, what is the relevance of this block diagram to the small gain theorem? I mean.
So this is a control system. You can understand this is your plant, this is your control. We didn't say this is uncertainty, this is a nominal model. But it can be anything. It can be anything. But in our case, I would like to remind you that so we can take everything m and k insert into here. So this is called, we are going to learn next, called LFT, linear fraction transformation. So basically this question reminds me, and this, so I can absorb everything in here, okay, everything here as a delta, as M structure, okay? So there is still a loop coming in here, right? There's a loop in here. So then I say that, so I have this M and K lumped to another one M, okay, lumped to this one. Let's say use P. Here I use M. Let's do a P here. So then, using the small gain theorem, I will be able to, because this is a given K, given M, this is a given, I know it. Therefore, it is, infinite norm is known to me. Therefore, based on a small gain theorem, I know how big this guy could be. Okay? Okay? So this is from robust performance or robust stability point of view. Okay? Point of view. But this is just a simple expansion of this M. So you lump all the stuff into the M. But you should understand this can be anything. So in this case, in our case, this is uncertainty. This is a lumped closed loop system. Okay? So in this case, M is none, because this is based on nominal model and your design K. So then I have W here. So then this is a small gain theorem. Then we can use this one to check how big my uncertainty bound could be. So that's very important. Another thing is, if I know the size of my delta, the infinite norm is gamma, then I can check whether the overall system is robustly stable, because I can examine the infinite norm of M, then see whether it satisfies small gain theorem. Okay, small gain theorem. So small gain theorem is very useful, very handy, especially in robust control. But I have a warning for you. This is really, small gain theorem is really kind of conservative in many cases, conservative. Okay? So you can see that the system, the loop always less than 1 is very, very suppressive. You really make the system bandwidth very small. Okay, very small. If you want to enlarge, then at some frequencies the gain will be greater than 0. So that's very interesting. I was reading last night. They said, oh, we did feedback control. So we did feedback control loop. Then actually, you know that when we say feedback, it's not very accurate, because at certain frequency, the phase might be over minus 180 degrees, because the phase plot is like that. So to those frequencies, they are actually positive feedback, right? Yeah? Yes. So if you say my system is always positive, always negative feedback, that's actually wrong. You should say, yes, I'm using a negative feedback for the signal, but at certain frequencies, some part of the signal components actually is positive. Make sense? Because you do for a series expansion, you know that a signal feedback, the signal contains many frequencies, and at certain frequencies, the phase actually pass 180 degrees. Then you got to reverse negative, negative, it will be positive. Okay? So when people say, oh, is it positive feedback bad? You should say, no, not really. Sometimes it's useful. I'm using this one to tell you that if you have some parts that the gain, loop gain, is always less than 1, fine. This could be conservative. And in certain frequency range, your gain could be greater than 1. Okay? Could be greater than 1. Then the system is still stable if the phase happens to be less than 180 degrees. So that's exactly the concept of gain margin, phase margin, okay, for the size of case. So in the gain phase margin, we didn't say, well, for system to be stable, the gain has to be less than 1. That's not right. So I'm not sure I'm confusing you or not. So let's take a look at a figure before we move on. So a typical system is gain. So this is 0 dB. So this is log 10 omega. So it's something like this. So this is called omega gain crossover. Okay. Omega gain crossover. So anything above is amplification. Anything so this is attenuation, right? So what I'm doing here is log 10 omega. So then I'm doing here is my phase. Okay. So my phase is usually 0 degree for the nothing. Okay. Then eventually this will go down. So this one. So this is minus 90, minus 180. So okay. So if I draw a case like this. So if I draw a case like this, so this is my. Let me do another color. So this usually low frequency is 0 phase. Then eventually it will go to. So say for example, this one is like very deep. Then this one will go to something like this. So this is called phase angle. It could keep going if you have infinity. It goes very, very big if you have delay in there. Okay? But here, when you cross this one here, so this one is called phase margin. Okay? It's called phase margin. And this one, when they cross this one, is called omega phase crossover. okay, phase crossover frequency. And this one corresponding to a value in here, so this magnitude here is less than 1, so negative, okay? So this distance here is called gain margin, okay? Gain margin, 1 over gain margin, okay? The reason we say 1 over gain margin is exactly due to this small gain theory. Okay, we didn't teach you on that, but it is true. So what I'm saying is, your system could be beyond 180 here, and all the signals here, okay, are actually doing positive feedback. Okay, positive feedback. So when you pass the 180 degrees, so all the signals here are doing positive feedback, isn't it? Let's do error. Error is my loop transfer function. Okay. So this is my L. Okay, magnitude of my L. Okay. So the signal here at this frequency here is all less than, the gain is less than 1. Although it is reversed sign. So across 180 degrees of reversed sign is becoming actual positive feedback. All the signal components here. But doesn't matter because the gain is less than 1. Okay? So make sense? However, I'm drawing another ugly system. That system is an unstable case. This system is something like this. So, okay, I do this, okay, but somehow okay, so somehow I do this. Okay, I do this. So when I cross over phase 180, 90 degrees to here, this corresponding to a point that is greater than 1. So my sign reversed, meaning I'm going to greater than 1, reverse, greater than 1, greater than 1, I keep doing this. So then I'm going to explode, right? So this is unstable case, okay? Because if I draw in here, gain crossover frequency here, to there I check my phase. Oh, my phase passed 180. Okay, that system is unstable. So the blue one is an unstable system. The black one is a stable system. And so gain phase margin type of concept, I hope you understand. And I want to clarify with you that although it's a negative feedback, you should understand that some frequencies, they are doing actually positive feedback. The reason you don't need to worry about it is because of the magnitude is so small. So it's attenuated. So the same idea here. Okay, I hope use this one to tell you that this overall actually infinity norm type of worst case scenario, a small gain theorem, is in fact could be very conservative. So just be aware, using small gain theorem could be conservative. Okay, but you don't have a better way to go. You just go with that. It's guaranteed to work. So then we can actually prove this one in the following way. So that's how many slides? So in fact, it's quite long. Let me see. So the reason we discussed this one is to be able to use it for robust performance and robust stability testing. So for example, the system is well posed or internally stable for all this one in H infinity with maximum value of this one is gamma. Okay. The system is well closed, internally stable for all the delta in the RH, and this one is also less than 1. So these are all valid. So these are all equivalent. Okay. All equivalent. So if you know your system worst case norm, H infinity norm, so it is a sufficient condition. When you say sufficient condition, I was trying to tell you this sufficient condition. Maybe you should say sufficient, but not necessary. Okay, understand? Sufficient, but may not be necessary. So that sufficiency is interesting, meaning this delta, you don't have to be LTI. Okay? Actually, it could be in general nonlinear time varying thing there. Okay? So because it's sufficient, that sufficiency will give you further help on those nonlinear time varying. If it is, of course, a stable operator. So let me do one thing with you. Say, for example, you have a control system, you have a plant, this is a nominal plant, this is a K, so you add this is your uncertainty is normalized to 1. So this is normalized to 1, less than 1, okay, less than 1. So we scale it or normalize it such that the infinite norm of this guy, delta, is something special with respect to delta. So it's nominal model, it's uncertainty normalized, let's say, normalized, scaled uncertainty that has actually infinity norm less than 1, okay? So then we know P, we know K, we know W1, we know W2, okay? We also know that actually infinite norm of W is, or delta is 1, okay? We know also that. So I want to ask, so this is feedback control interpretation. I want to ask, there are infinitely many plants in here, and the K originally stabilized this one. Then after I had this one, and whether the system is still robustly stable, how to do that? Again. So if we discuss this way, it is difficult to discuss. But if we discuss in such a way that, what do? You pull out the delta, put this delta out, the rest is something you know. Everything is known, okay? K is known, W1, W2 is known. So these are our known weighting filters, not only for scaling of this or normalization of the delta, but also to bring in your designer's requirements or put different emphasis to different frequency range, high frequency, low frequency, high pass, low pass, and so on and so forth. And these are the sensitivity transfer functions like output, input, this complementary sensitivity function. So these things, I think we know that. Whenever you see this, you are going to, so this is SO here. So SO is this one. So it's I plus PK inverse. Then you have this K in here, W in here, W. So you can do this separation here. And this minus sign should be absorbed in here, okay? Then you do this. So you do this. So this is something called robustness evaluation. So this needs the separation of uncertainty and known models. So then what are you going to do? You know the size of this one is less than 1. Okay? So according to small gain theorem, the norm of this guy should be less than 1. If and only if. Okay? So this is our uncertainty set. So the uncertainty set. So you can see that small gain theorem enables us to discuss this internal stability or will-posedness in face of uncertainties, and check whether this is true or not. But what if this is not true? What you should do? You should tune the K, right? You design the K. Tune that K such that this is true. So you make this system. So we are addressing, this is easily used to address the nominal stability and robust stability. We haven't talked about performance yet. Okay?
Dr. Chen, W1 and W2.
It's of your choice. You can also choose W1 and W2. If you don't have a good idea, you just put them as an identity I and I. Okay? But you can choose W1, W2.
Like weight day uncertain?
No, they are exactly known. It's not uncertain.
No. I mean, the function is weight day uncertain. The
Yeah,
uncertainty.
it's to do normalization or do scaling or conditioning
Mhm.
or massaging that uncertainties.
I think we should extract W1 and W2 so that norm infinity of delta is less than 1, right?
Yeah, that's the purpose.
Exactly.
Otherwise, you cannot write directly to 1. This needs some normalization or manipulation. Of course, you have seen that there are more than one ways to write this type of uncertainty set. This uncertainty set, if you do a good job, it is small. If you do a bad job, it's unnecessarily big. Then make your controller and design more conservative. Okay. So this is the one additive uncertainty case. So let's see a multiplicative case. Multiplicative case, you have a P on this side, W2 in here this side. Okay, so it's like a gang.
So the additive uncertainty needs the sensitivity function, and this one use the complementary sensitivity.
Yes, yeah, you are right. This can be derived. This can be derived easily. Easily. Just follow the signal flow and be careful about left multiplication and right multiplication. That's in the minor case. Then you easily get to here. Okay. I'm
So-
not going to derive that.
So this is general case for minor. This
Yes, this is all MIMO case. This is all MIMO. So this is also a MIMO case, okay? All MIMO case. You may ask, say, hey, look, you did this side, can we do in front side? The answer is yes, you can do it. Just, what if your P is not square? Okay. Could be a not square. So let's assume this is true. We do this one, and I want to pull out this delta. Pull out the delta, keep it here, and the rest will be in here. And the rest can be written in this format. And fortunately, we just decide this is out, this is in. All others are just inside the box. Then you'll get just right. Again, this is considered as easy. It is easy to get. And we are going to have homework to practice this thing, okay? Practice this thing. So this is called kind of additive, and then we can leverage this small gain theorem. Again, I hope you remember this picture I have drawn here. I'm very familiar with this one. The reason is it's so important for us to understand for size of case, what is stable, what is unstable, and how much stable, how far away you are from unstable, being unstable. So these are very important questions. And you guys probably heard about this. What is the gain margin? Gain margin is 1 over this distance. 1 over this distance. round over that distance is exactly the small gain theorem. Okay. All right, so let's see these two, then I'm going to stop and I'll let you go. So there's also what we call co-prime factorization uncertainty. So you have it's not, okay, let's say this. So we have a nominal plant, we have a stable left co-prime factorization. And how to do this one? We have commands in MATLAB. Amounts to solve LQR problem. Please revisit the textbook, there's a procedure. And I think that there's one question in homework, so please practice. Giving a transfer function matrix, how you can do this co-prime factorization. Okay. Then you stabilize that. So this M-tiered, N-tiered. So you contain uncertainties in M, uncertainties in N. So this is a co-prime factorization uncertainty. This is something not less familiar to many people, but I hope we have some practice on this one. And for each of this uncertainty, we'll assume this is also in RH infinity. So then we still assume this is the RH infinity norm less than 1 if you have this infinite norm. You have, so this is, remember you have a block diagram, K stacked with I here, because this is kind of 2 here, the size is bigger. Okay, and also you need inverse of M. So this is the left co-prime. You can do right co-prime factorization. Okay. Again, I remind everybody here. This is RH infinity. This is RH infinity as well. In other words, so you have a transfer function matrix. You want to write into 2 transfer function matrices. One is this guy N, one is this guy M. M has an inverse on the left, and both M and N tiered are in RH infinity. Okay, RH infinity means I use this RH infinity. Yes, infinity. Okay, check that chapter. What does this mean? It's a stable, strictly proper transfer function matrices. Okay. So this is a generalization of the concept of numerator and denominator in a MIMO case. And remember, we are talking about 2 matrices here. Okay, 2 matrices, and each of them are RH infinity. Okay, RH infinity. So be careful. Okay, because it's quite different to a Celsius case. Okay, so let me show you this one, and we are going to. So we see we have perturbation model set. So W1, W2, delta, and delta infinity norm less than 1. So you have this K and P, and you have description case. So this is on the left, this is on the right. Okay, you have also inverse format. So it depends. Sometimes may say high frequency, low frequency, dynamics answer in RHP zeros. RHP stands for right half plane. Right half plane. Again, I hope you never use unstable zeros, because 0 has nothing to do with stability. So you should not say unstable, you should say right half plane. The zeros in the right these are talking about high frequency dynamics, low frequency parameters, and so on and so forth. So these things, like, this is the format, this is another format. So then you will see what's the difference. It's the same, but it's TO, the TR, okay? And then you have inverse. So look at this one to this one. It's like inverse. So then you'll see inverse part compared to this, you are going to have the same instead of T. T is a complementary sensitivity function. S is a sensitivity, output sensitivity function. So you can verify this one by careful manipulation using this separation principle, pull out and leave all this thing rest, and this is the rest. Okay, this is the rest, and you can define all different structures of this, different structures in here. Then you will have different conditions. So that is for stability checking. Say. So this is something like this. I have a system, nominal system. You design a controller, make it stable. Then I want to see, when I have additional uncertainties, whether it will still be stable. So it's a NS, the nominal stability design for K. Then check R as robust stability for this, okay? So we have learned a trick. Then the important background is small gain theorem, okay? And in the MIMO setting, you just be careful about this sensitivity transfer functions. And next lecture, we will start by talking about robust performance. Okay, we'll talk about performance, nominal performance and robust performance. Okay, so with that, we stop here and we're going to talk about robust performance next time. Okay, thank you.